Welcome to today's problem walkthrough. We're diving into LeetCode problem number 1036, Escape a Large Maze. This is a fascinating challenge that combines graph traversal techniques with optimization strategies. Let's explore the problem, dissect the approaches, and work through the solution together. The problem involves navigating a massive grid, which is 1 million cells wide and 1 million cells tall. Each cell in the grid can either be open, meaning you can walk through it, or blocked, meaning it's an obstacle you cannot pass. The grid is sparse, so most cells are open, but the blocked cells can make the path tricky. You are given a starting point, called the source, and a destination point, called the target. The goal is to determine whether it's possible to move from the source to the target while avoiding the blocked cells. Movement is restricted to one cell at a time, and you can only move in the four cardinal directions: up, down, left, or right. To solve this problem, you are given three inputs. The first is a list of blocked cells, where each blocked cell is represented by its coordinates on the grid. The second is the source cell, which contains the starting coordinates, and the third is the target cell, which contains the destination coordinates. Your task is to return true if the target is reachable from the source, and false if it is not. Let's look at the first example to understand the problem better. Here, the blocked cells are at coordinates 0, 1, and 1, 0, the source is at 0, 0, and the target is 0, 2. The output is false because the source and target are separated by the blocked cells. Specifically, the blocked cells create a small region around the source that prevents any movement toward the target. In this case, the grid is effectively limited to a very small area around the source, making it impossible to escape the blocked region and reach the target. Now consider the second example. In this scenario, there are no blocked cells, and the source is at 0, 0, while the target is at 999,999, 999,999, almost the opposite corner of the grid. The output is true because, without any obstacles, the source can freely traverse the entire grid to reach the target. This example demonstrates that when no cells are blocked, the problem reduces to simple navigation across the grid, no matter how large the distance between the source and target. In the third example, the blocked cells are near 10, 10, forming a small cluster. The source is at 0, 0, and the target is at 100, 100. The output is true, as these blocked cells do not form a large enough region to trap the source. While the blocked cells might restrict movement in a specific area, the grid itself is so vast that there are plenty of alternative paths to bypass the obstacles and reach the target. This example highlights that small clusters of blocked cells are unlikely to prevent movement across the grid unless they form a much larger, enclosing structure. The problem also comes with a few important constraints and edge cases to consider. First, there can be up to 200 blocked cells, or none at all. The coordinates of the source and target, as well as the blocked cells, must all lie within the bounds of the grid, from 0 to 10⁻6, 1. Additionally, the source and target cells themselves will never be blocked. Edge cases include scenarios where there are no blocked cells, which means the result is always true since the source can freely navigate to the target. When the blocked cells form a small trap, the source can often escape, but if the blocked cells form a large enough region to completely surround the source or target, escape becomes impossible. Finally, the problem must efficiently handle cases where the source and target are very far apart, such as being located in opposite corners of the grid. These considerations will influence how we approach solving the problem and designing an algorithm to handle all possible scenarios. To solve this problem, the first approach that comes to mind is to use a brute force method, such as breadth-first search or depth-first search. In this approach, we explore the grid starting from the source cell and continue until we either reach the target cell or exhaust all possible paths. However, given that the grid size is 1 million by 1 million, this strategy quickly becomes computationally infeasible. The sheer number of cells makes it impossible to store all visited nodes or process every reachable path within a reasonable amount of time. Even though most cells are open due to the grid's sparsity, blindly traversing the entire grid would result in excessive memory and time usage. Instead, we can refine our approach by focusing on key observations that reduce the problem size. First, the sparsity of blocked cells means that movement is constrained primarily by these blocked cells, not the size of the grid itself. With at most 200 blocked cells, the problem simplifies to checking whether these cells create a barrier that prevents the source from reaching the target. Second, the maximum area that can be enclosed by these blocked cells is relatively small, about 40,000 cells. This means that if the source or target is encircled by blocked cells, escape becomes impossible. These observations allow us to shift our focus to localized regions rather than the entire grid. Building on these observations, we can develop an optimized approach using a multi-level BFS. Instead of attempting to traverse the entire grid, we treat the blocked cells as barriers and limit our BFS to a small region around the source and the target. The strategy involves two critical checks. First, we use BFS to determine whether the source can escape its surrounding area by reaching at least 200 by 200 cells. This ensures the source is not enclosed by blocked cells. Second, we perform the same check for the target, ensuring it is not similarly enclosed. If both the source and target regions are sufficiently large and overlap, we can conclude that the source can reach the target. However, if either region is too small or the two regions are disjoint, escape is impossible. By limiting the BFS to these localized regions, the computational requirements are drastically reduced while still guaranteeing accuracy. The chosen strategy is driven by the intuition that exhaustive traversal of the massive grid is not only impractical but also unnecessary. The grid's sparseness means that the only way escape can fail is if the source or the target is completely surrounded by blocked cells. By focusing solely on regions near the blocked cells, we significantly reduce the problem size while still capturing the essential constraints. This approach is efficient because the BFS is limited to a maximum of approximately 40,000 cells, making it computationally feasible. It is also correct, as it independently verifies the accessibility of the source and target regions and ensures they overlap, covering all cases where escape is possible. However, there are trade-offs. While memory usage is manageable due to the reduced region size, we still need to track visited cells within these regions. Additionally, we must handle edge cases carefully, such as when the source or target is directly adjacent to blocked cells. When compared to alternatives, a naive BFS or DFS would fail due to the grid size, and more advanced algorithms like A** are unnecessary because the problem has already been simplified by focusing on potential enclosures. Finally, let's analyze the time and space complexity of this approach. The time complexity is O(B), where B represents the number of reachable cells within the blocked regions. In the worst case, this is approximately 40,000 cells, making the method computationally efficient. Similarly, the space complexity is also O(B), as we store the visited set for BFS within the localized regions. This balance of efficiency and feasibility makes the strategy well suited for the problem, ensuring that we can check for escape possibilities without being overwhelmed by the grid's massive size. In this problem, we are working with a grid that is 1 million by 1 million in size. The objective is to determine if we can navigate from a given source cell to a target cell. However, the sheer size of the grid makes traditional traversal methods like breadth-first search or depth-first search infeasible, as they would require far too much computational time and memory. To solve this problem more efficiently, we need to consider optimized techniques. One such approach is bidirectional BFS, which significantly reduces the area we need to explore by starting the search simultaneously from both the source and the target, with the two searches meeting in the middle. This is a powerful strategy to handle the challenges posed by the massive grid size and the presence of obstacles, while adhering to the constraints of moving only in the four cardinal directions: up, down, left, and right. To implement bidirectional BFS, we first need to set up the right data structures. Specifically, we use two queues, one for exploring the grid from the source cell, and another for exploring from the target cell. These queues, named Q_source and Q_target, will hold the cells currently being processed during the search. Alongside the queues, we maintain two hash sets, visited_source and visited_target, to keep track of cells that have already been visited by their respective searches. This prevents redundant exploration and ensures efficient lookup times. Each cell in the grid is represented as a coordinate pair, such as x, y, and we assume all cells are traversable unless explicitly blocked. With these structures in place, we initialize the queues with the source and target cells, marking them as visited in their respective hash sets. This setup prepares us to begin the bidirectional BFS process. The bidirectional BFS involves iterative exploration until either a path is found or both searches are exhausted. While both queues are non-empty, we alternate between expanding from the source and expanding from the target. Starting with the source, we dequeue the front cell from queue_source and examine its neighbors in the 4 cardinal directions. For each valid neighbor, if it is already in visited_target, it means the 2 searches have met, and the target is reachable. Otherwise, if the cell is unvisited and not blocked, we mark it as visited and in-queue it for further exploration. Similarly, we then expand from the target by dequeuing the front cell from queue_target and repeating the same process, checking for intersections with visited_source. This dual expansion ensures that the searches converge quickly, minimizing the number of cells we need to process. If at any point the 2 visited sets intersect, we can terminate early and confirm that a path exists. If, instead, both queues are exhausted without any intersection, we conclude that the target is unreachable. Bidirectional BFS is particularly effective for large-scale problems like this because it drastically reduces the search space compared to a standard BFS. In a normal BFS, the search expands outward from the source, covering all reachable cells, which can be computationally prohibitive for a grid of this size. By contrast, bidirectional BFS splits the work in 2, with each search covering only half the distance before meeting in the middle. This reduces the time complexity from OK to approximately OK⁻², where K is the number of traversable cells. Another key advantage is early termination. The algorithm stops as soon as the 2 searches intersect, avoiding unnecessary exploration. The use of hash sets for visited cells ensures constant time membership checks, which is crucial for efficiency, while queues facilitate orderly processing of cells in a first-in first-out manner, making them ideal for BFS traversal. The success of bidirectional BFS relies on 3 core data structures. First, queues are used to manage the frontier of cells being actively explored, allowing us to in-queue new cells and dequeue cells for processing in a systematic way. Second, hash sets are essential for tracking visited cells during the search. They enable constant time operations for adding new cells and checking whether a cell has already been visited, which is vital for avoiding redundant computations. Lastly, grid cells are represented as coordinate pairs, such as x, y, making it straightforward to manipulate and store them in the queues and hash sets. These data structures work together seamlessly to ensure that the algorithm remains efficient and scalable, even for the massive grid size and complex obstacle patterns found in this problem. Analyzing the complexity of this approach, the time complexity is determined by the number of reachable cells, denoted as K. Bidirectional BFS reduces the search space to approximately OK⁻², as each search only needs to cover half the distance before meeting in the middle. The space complexity is similarly OK⁻², as we need to store the visited cells for both directions. This makes the algorithm significantly more efficient than traditional BFS for large grids. Regarding edge cases, there are several to consider. If the source or target cell is blocked, we can immediately return false, as no path is possible. If the source and target are the same cell, we can directly return true. Finally, in situations where the path is completely obstructed by obstacles, the algorithm will terminate correctly without entering an infinite loop. These considerations ensure that the solution is robust and handles all scenarios appropriately. Here, we begin implementing the solution to determine if it's possible to escape the large maze. We start by defining a class called solution, and its method is escapePossible, which takes 3 parameters: the list of blocked cells, the source position, and the target position. The first thing we check is whether the blocked list is empty. If it is, escaping is always possible, so we return true immediately. Next, we calculate a critical value called blocked_limit. This represents the maximum number of nodes we need to explore to confirm that our path is not constrained by the blocked cells. It's derived from the formula for combinations, considering the number of blocked cells. We then define the potential directions for movement up, right, down, and left using coordinate offsets. To efficiently check if a cell is blocked, we convert the blocked list into a set called blocked_set, as set lookups are faster than list lookups. After setting up these preliminaries, we define a helper function BFS, which uses breadth-first search to explore the maze starting from a given position. Inside the BFS function, we initialize a visited set to keep track of cells we've already explored and a queue to manage the cells we need to process. The starting position is added to both the visited set and the queue, and we initialize a counter to track the number of cells we've explored so far. The main loop of the BFS begins by dequeuing the next cell and incrementing the counter. If the counter exceeds the blocked underscore limit, we conclude that the exploration area is unconstrained, and we return true. Now, inside the BFS loop, we iterate through all possible movement directions. For each direction, we calculate the coordinates of the next cell by adding the direction offsets to the current cell's coordinates. We then check several conditions. The new cell must be within the valid maze boundaries, it must not have been visited already, and it must not be in the blocked underscore set. If these conditions are met, we check if the new cell matches the target position. If it does, we return true immediately since we've found a path to the target. Otherwise, we add this new cell to the queue for further exploration and mark it as visited. If the loop completes without finding the target and without exceeding the blocked underscore limit, we return false, indicating that the path is constrained. Finally, the isEscapePossible function concludes by calling the BFS function twice, once from the source to the target and once from the target to the source. This ensures that both the forward and reverse paths are feasible, as the presence of blocked cells could constrain movement in one direction but not the other. If both BFS calls return true, the function returns true, confirming that escape is possible. Otherwise, it returns false. Here, we start by importing the necessary libraries and defining the class solution. To handle the constraints of the problem effectively, we set up some constants. Max_chord represents the maximum possible coordinate value, which is 1 million, and blocked_limit is calculated based on the maximum number of blocked cells to determine when an area is sufficiently surrounded. The directions array helps us navigate in 4 possible directions: up, down, left, and right. The main method, isEscapePossible, takes the list of blocked cells, along with the source and target positions. If there are no blocked cells, we can immediately return true, as there's nothing obstructing the path. Otherwise, we store the blocked cells in a hash set for efficient lookup. The solution to the problem is determined by performing a breadth-first search, or BFS, twice, once from the source to the target and then from the target to the source. This ensures that we account for cases where one direction might be open, but the other is enclosed. Now, the BFS method begins by initializing the necessary data structures. We use a hash set to keep track of visited cells in a queue for the BFS traversal. The starting position is added to both the queue and the visited set. We also initialize a counter to track how many cells we have explored. Inside the BFS loop, we process each cell by dequeuing the current position and incrementing the counter. If the counter exceeds the blocked_limit, we can conclude that the area is not fully enclosed by the blocked cells, so we return true. For each cell, we attempt to move in all 4 directions using the directions array. The next position, defined as NX in New York, is validated to ensure it lies within the grid boundaries. We then construct a unique key for the position and check if it has already been visited or is blocked. If not, and if the position matches the target, we can return true immediately. Otherwise, we add the position to the queue and mark it as visited. Finally, once the BFS loop ends, if we haven't been able to reach the target and the blocked_limit condition wasn't satisfied, we return false. This indicates that the target is inaccessible due to the blocked cells completely enclosing the area. This complementary check ensures that both the source and target are reachable under the given constraints. With this, the implementation is complete, and the BFS logic handles the traversal while efficiently checking for enclosures within the constraints of the problem. In this example, we are working with a small maze where there are no blocked cells. The input specifies an empty block list, and the source is at 0, 0, while the target is at 999,999, 999,999. Since there are no obstacles in the maze, it is guaranteed that a path exists from the source to the target. As a result, the function immediately returns true without performing any further checks or computations. This highlights the simplest case, where the absence of blockages ensures an unobstructed path. Now, let's consider a scenario where the maze has a small blocked area. Here, the input specifies 3 blocked cells, 0, 1, 1, 0, and 1, 1. The source is at 0, 0, and the target is at 0, 2. To begin, the blocked underscore limit is calculated as 3, which represents the maximum area that the blocked cells can enclose. The blocked cells are stored in a set for quick access during traversal. Since both the source and the target are in close proximity and there are blockages, we need to perform two breadth-first search (BFS) operations, one starting from the source and another from the target. This two-sided BFS approach helps confirm if there is a viable path between the 2 points. Starting with the first BFS from the source, 0, 0, we initialize the queue with the source cell, mark it as visited, and set the exploration count to 0. In the first iteration, we dequeue the source cell, increment the count to 1, and check its neighbors. The neighbor at 0, 1 is blocked, as is the neighbor at 1, 0. The other two neighbors, 0, -1, and -1, 0, are out of bounds. With no valid moves remaining, the BFS ends, and we determine that the target cannot be reached from the source. Since the path is blocked in one direction, there is no need to perform the second BFS. The function returns false, indicating that escape is not possible in this scenario. Let's examine a larger maze where the target is reachable. The input specifies two blocked cells, 0, 1, and 1, 0. The source is at 0, 0, and the target is at 999,999, 999,999. First, the blocked underscore limit is calculated as 1, which is based on the number of blocked cells and their potential to enclose an area. The blocked cells are stored in a set for efficient lookup. As before, two BFS operations will be performed, one from the source to the target and another in the reverse direction. This ensures that we can explore the feasibility of escape from both perspectives in this much larger maze. For the BFS starting at the source, 0, 0, we initialize the queue, visited cells, and the count. In the first iteration, the source is dequeued, and its neighbors are checked. The cells, 0, 1, and 1, 0, are blocked, while the other two neighbors are out of bounds. Despite the lack of valid moves from the source, the BFS concludes that escape is still possible because the count of explored cells exceeds the blocked underscore limit. This indicates that the maze is too vast for the blocked cells to completely trap the source. A similar BFS conducted from the target confirms the same conclusion. Both BFS results affirm that there is a path, and the function returns true, confirming that escape is achievable in this case. To analyze the time complexity of our solution, we begin with the breadth-first search, or BFS, which is carried out from both the source to the target and vice versa. First, we calculate the blocked underscore limit. This value is derived as the product of the number of blocked cells in the grid, multiplied by 1 less than that number, divided by 2. Since this calculation involves simple arithmetic, it has a constant time complexity of 1. Next, we convert the blocked list into a set, referred to as blocked underscore set. This conversion takes linear time, or OB, where B represents the number of blocked cells. Using a set here is essential because it allows for constant time, or O1, lookups during the BFS. Finally, the BFS itself proceeds layer by layer, exploring neighboring cells. The process terminates early either when the number of visited cells surpasses blocked underscore limit or when the target cell is found before reaching this limit. This ensures we minimize unnecessary exploration in the grid. Now, let's examine the time complexity of the BFS in more detail. In the worst-case scenario, the BFS visits up to blocked underscore limit cells. For each cell, processing includes verifying grid boundaries, checking the visited set, and adding unvisited neighbors to the queue, all of which are constant time operations. Thus, one BFS call has a time complexity of O, blocked underscore limit, which simplifies to O, B squared, because blocked underscore limit equals B times B1, divided by 2, which grows quadratically with B4 large values. Since the algorithm performs two BFS calls, one from the source to the target and another in reverse, the total time complexity becomes 2 times O, B squared, which simplifies to O, B squared. When we consider the entire solution, the BFS dominates the time complexity, resulting in an overall time complexity of O, B squared. Shifting to space complexity, the blocked underscore set requires O, B, space to store the B blocked cells. During the BFS, the visited set keeps track of up to blocked underscore limit cells, requiring O, B squared, space in the worst case. Similarly, the BFS queue can grow to store the same number of cells, also requiring B squared space. In addition to the blocked_set, visited set, and BFS queue, the algorithm uses a few constant space variables, such as blocked_limit, directions, and counters, which contribute 1 space. Therefore, the dominant space usage comes from the visited set and the BFS queue, giving an overall space complexity of B squared. Considering the best, average, and worst-case scenarios, in the best case, if there are no blocked cells or if the source and target are directly reachable without significant obstacles, the BFS terminates early. Here, the time complexity reduces to min distance B squared, and the space complexity is B, since minimal exploration is required. On average, the BFS explores up to blocked_limit cells, leading to a time complexity and space complexity of B squared. In the worst case, when blocked cells form a dense region around the source or target, the BFS reaches its maximum exploration limit of blocked_limit cells, resulting in B squared time and B squared space. When comparing our optimized approach to a brute force solution, the difference is significant. A naive approach would attempt to explore all reachable cells in the grid, which consists of 10 to the power of 6 by 10 to the power of 6 cells. This results in a prohibitive time complexity of n squared, where n equals 10 to the power of 6. By contrast, our solution limits exploration to blocked_limit cells and uses BFS for systematic and efficient traversal. This reduces the time complexity to B squared, which is far more manageable. The mathematical justification for this lies in the behavior of BFS, which explores no more than blocked_limit cells. Additionally, the visited set and BFS queue grow proportionally to the number of cells visited, also resulting in B squared space. Using a set for blocked ensures 1 lookups, eliminating unnecessary overhead. Overall, this optimization ensures that the algorithm is both time efficient and space efficient, making it suitable for handling reasonable input sizes within the given constraints. One of the most common mistakes when solving grid problems is overlooking edge cases. For example, what happens if the grid is empty, has just one cell, or if the source and target are the same? Ignoring these scenarios can easily lead to runtime errors or incorrect outputs. To avoid this, you should explicitly validate your input and handle such cases right at the beginning of your implementation. Another frequent error is not marking nodes as visited during traversal. If you don't keep track of visited nodes, your algorithm might revisit the same node repeatedly, causing infinite loops or incorrect results. To prevent this, you can maintain a separate visited matrix or directly modify the grid itself to mark nodes as visited. Finally, using inefficient traversal methods can also lead to issues. For instance, depth-first search isn't suitable for finding the shortest path in unweighted grids because it doesn't consider distance. Instead, breadth-first search is a better choice for such tasks, as it explores all nodes at the current depth before moving deeper, ensuring that the shortest path is found. Another common pitfall is poor handling of obstacles or weighted grids. For example, if your algorithm doesn't properly skip blocked cells or account for weights, it might traverse incorrectly, leading to invalid results. The solution here is to adjust your traversal logic to avoid blocked cells and, for weighted grids, use algorithms like Dijkstra's that incorporate a priority queue to handle weights effectively. Another issue arises when developers assume the grid is always well-formed. For instance, if you assume every row has the same number of columns or fail to check for malformed inputs, you might run into index out-of-bounds errors. To address this, always validate the grid structure before beginning your processing. These checks may seem minor, but they're crucial for building robust and error-free solutions. In interviews, it's vital to showcase your problem-solving approach. Start by discussing edge cases. For example, ask about grid boundaries, whether obstacles are present, and if diagonal movement is allowed. This shows that you're thinking critically about the problem. It's also important to optimize based on constraints. If the grid size is very large, brute force solutions won't work. Instead, use efficient methods like BFS for unweighted grids or A** for weighted ones. Additionally, be ready to discuss space versus time trade-offs. For instance, using a visited matrix increases space usage but makes the logic cleaner, whereas modifying the grid in place saves space but can be harder to debug. Finally, Think modularly by breaking your solution into reusable functions, such as one for finding valid neighbors. This demonstrates clean coding practices. For further practice, you can explore related problems like LeetCode 200 for finding islands, or LeetCode 1091 for the shortest path in a binary matrix, all of which share similar concepts. When considering alternative approaches, the A** search algorithm is a powerful option for finding the shortest path in weighted grids. It uses a heuristic, such as Manhattan distance, to guide the search, making it more targeted than BFS. However, A** is computationally more expensive and relies heavily on the quality of the heuristic. For problems focused on connectivity rather than pathfinding, the union find algorithm is another alternative. It's particularly efficient for static connectivity checks, as it avoids repeated traversals. However, adapting it to handle dynamic changes can be challenging. Lastly, for problems where the goal is to count paths instead of finding them, dynamic programming is a great choice. By using memoization, you can avoid redundant calculations and improve efficiency. Of course, this comes at the cost of additional space usage. Each of these approaches has its strengths and trade-offs, so it's important to pick the right tool based on the problem at hand. Great work! Today, we tackled a complex maze problem, sharpening our skills in graph traversal and optimization. Remember to focus on reducing unnecessary computations and leveraging problem constraints. Thanks for joining, and see you in the next problem walkthrough. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!